Our first lesson in the periodic table and bonding unit is on the development of the modern periodic table. So our learning targets for this lesson, three of them. We want to recognize and explain the need for an organizational system for the elements and their properties. We want to demonstrate and explain the workings of the first periodic tables. And we want to state and differentiate Mendeleev's periodic law with the modern periodic law. Learning target number 1. So, in the late 1700s, the chemist by the name of Antoine Lavoisier, he compiled a list of all 33 known elements, and he compiled them into 4 categories. And here you can see his list. Now you'll notice that it is in French, because Lavoisier was a Frenchman. If you look carefully, you'll see some elements that you probably recognize, even though the spellings might be a little different because it is in French. You'll notice here we have antimony, and we have arsenic and cobalt and manganese, mercury, nickel, okay, things that you're probably familiar with. Also things that you're familiar with that you probably just don't recognize the names would be something like argent. That would actually be gold. Or we have platinate, that would be platinum, and plomb would be lead. So we can see some very, very familiar metals here to us. A lot of these elements had been known since ancient times. And after Lavoisier comes up with his list, as time goes on, we get to the 1800s, of course, and this brought on a very large increase in the number of known elements. Things like the advent of electricity that allowed us to start to break compounds down into their components, and the development of an instrument known as the spectrometer, which allowed us to identify newly isolated elements. And then the Industrial Revolution, that brought on many chemistry-based industries, which helped us discover even more elements. So we get to the late 1800s, roughly 1870, and there are about 70 known elements. All of these new elements and technologies meant that we had new data that we had to sift through. There was a lot more that we had to know. This became very overwhelming to learn for chemists and other scientists of the day. And so there became a need to have a tool for organizing all of the facts about all of these new known elements and all their properties. One of the things that led to our ability to organize these facts was the fact that in 1860, chemists in Europe mostly agreed upon one method for determining the atomic masses of elements. Now, these atomic masses would not be the same thing that we know today as atomic mass, but it was a very similar thing to it and a precursor to what we now know as atomic mass. Before then, different chemists had a different way of calculating these masses, so it was almost impossible for a chemist in one lab to get the same results as a chemist in another lab, simply because he or she was working with a different set of atomic masses because they had their own way of calculating them. But whenever chemists started to agree upon these things, it allowed them to start to speak a more common language and thus come up with a common organizing tool. So that's the first learning target. We've seen why we need to have an organizational system for elements and their properties to go along with them. So now we want to be able to demonstrate and explain the workings of the first periodic tables that came to existence. First, from a gentleman, an English chemist by the name of John Newlands. In 1864, he proposed an organizational scheme. What Newlands recognized was that whenever he arranged the elements by increasing atomic mass, their properties repeated every 8th element. So in other words, if he ordered all the elements from the lowest atomic mass to the highest, that every time he got to the 8th element, the properties would seem to start over again. Not exactly the same, but very similar. So here's a picture of this Newlands character along with his organization. So you'll notice here that the elements are ordered here by their atomic mass, and just ordered 1, 2, 3, 4, 5, 6, 7. Those numbers there do not represent the masses of the elements, just the order that they come in. And then you can see the symbols: hydrogen, lithium. G is an element that we now know to be beryllium. It wasn't called that at the time. We have boron, carbon, nitrogen, oxygen. And then every eighth element, the pattern repeats. In other words, hydrogen had similar properties to fluorine, which had similar properties to chlorine. Likewise, lithium was similar to sodium, which is similar to potassium. So every eighth element, these properties, they would tend to start over. In other words, this idea is known as a periodic property, simply because it's something that repeats in a specific manner. In this case, the manner being every eighth element. Newlands would name this relationship the law of octaves. The reason he called it the law of octaves is this worked the same way that a music scale does, where every eighth note you get back to the same note you start with. So if you start a scale on an A, by the time you get to the next A, then you're an octave above it, and that's 8 notes later. The problem for Newlands, and for the rest of the scientific world, is this law of octaves was not well accepted. For one reason, it did not work well for all elements. You'll see here in the table that he had to put 2 elements in some spots, and in other places the properties really were not that similar, or they did not repeat that well, and so it didn't work real great, the whole law of octaves. Another reason it wasn't very well accepted was just because Newlands chose to use the term octave. It was not seen as a scientific term, that the terms we use in music and art shouldn't be applied to science, and so a lot of his ideas got discarded, which was unfortunate because Newlands was basically correct in his thinking. Some of the details were not necessarily correct, but a lot of his thinking was absolutely spot on, as we'll find out. So the next development in what eventually became the modern periodic table came from 2 scientists, and they did this independently. In other words, they were not working together, but they came to virtually the same result. The scientists by the name of Lothar Meyer, an English chemist, and Dmitry Mendeleev, a Russian chemist, and they both independently demonstrated in the same year, in 1869, very same connection that Newlands did, a connection between atomic mass and the properties of elements. Now, from here on out, I'll just refer to Mendeleev because he is given more credit for this since he published his work first. Scientific discovery, even today, is essentially a race. The first person or first group of scientists that can publish, that can get their ideas out there, are the ones given credit for it. So history will always look at Mendeleev as being the developer of the first modern atomic or first modern periodic table, even though he and Meyer essentially came up with the same thing at the same time. So Mendeleev basically did the same thing that Newlands did before. He arranged the elements in order by their increasing atomic mass, and this showed him that there was a periodic pattern to the properties. In a predictable way, the properties seemed to repeat. So here's a picture of Mendeleev's table. It's not quite as easy to look at as the one on the previous slide from Newlands, but just to demonstrate what we're seeing here, so we have the lightest element here, hydrogen, and now these numbers, so note it says hydrogen equals 1, and then below that lithium equals 7. Those numbers are the atomic masses of the elements, or at least the atomic masses that were used at the time. If you look at your modern periodic table that you have, you will notice that these numbers do match remarkably well with what we use today for most of these elements. And so what Mendeleev recognized is that whenever he ordered these by their atomic mass, so hydrogen was the lightest element, and then came lithium, and then after lithium was beryllium, boron, carbon, you can see how it goes, that every so often, after fluorine, then we get to sodium, that sodium's properties were very similar to lithium's. And then we start the pattern over, or magnesium, aluminum, etc., again ordered by atomic mass, and then we get to potassium, and the properties were very similar to sodium. So when he ordered them this way, elements that were in the same column had similar properties. In other words, it wasn't just this first column, hydrogen, lithium, sodium, etc., that had similar properties, but so did the second column, and the third, and the fourth, etc. Now, one thing you'll notice as you look at this table is that there are blanks. There are many blanks, actually. Some even have listed atomic masses. For example, if you look here below aluminum, you see an element that's left blank, but that has a listed atomic mass of 44. Likewise, below that, there's a blank one for a listed atomic mass of 68, and one here to the right of 72. Mendeleev was forward-thinking enough that he recognized that there would be more elements that would be discovered after he published his periodic table. And so what he did was he looked at the patterns of the properties that already existed, and he was able to predict those properties of elements that had not yet been discovered. So in other words, these atomic masses that you're seeing here were not just wild shots in the dark. These were predicted by Mendeleev by his calculations that he did working with the properties of the elements that he already knew. This was one thing that led to a very wide acceptance of Mendeleev's periodic table. Unlike many other scientific ideas, his new idea for organizing the periodic table was widely accepted throughout the scientific community because it was so accurate, and it did such an unbelievable job of predicting the properties of elements before they were even being discovered. As these new elements did start to be discovered, scientists started to realize that Mendeleev was very accurate with his predictions, and so it told them that this periodic table was probably pretty darn good. Now, another thing that Mendeleev had to do was he did have to reverse the order of some of the elements. So, in other words, he did start by ordering them by increasing atomic mass, but there were some elements where he actually had to reverse the order of in order to make the pattern stick. In other words, in order to make the pattern continue, those periodic properties continue to hold, he had to reverse the order. And Mendeleev thought that this was simply because that those atomic masses were not yet measured correctly. He recognized that the technology of the time was not the greatest, and that over time, as technology improved, that it would be shown that the order that he had was actually the right order for atomic mass. This is one thing he actually did not end up being correct about. So one way to summarize all of this stuff about Mendeleev and his table is to state what we now call Mendeleev's periodic law. And that is simply that the properties of the elements are periodic functions of their atomic masses. In other words, when we order all the elements by their atomic mass, there are properties of those elements that they repeat in a predictable way. In this case, every 7 elements or so. Alright, so we've looked at the workings of the first periodic tables from Newlands and then Meyer and Mendeleev. Now we want to look at a more modern view of how our periodic table works today. So the English physicist, and he was actually also a doctor by the name of Henry Moseley, in 1913, so a little over 100 years ago, he discovered that every element contains a unique number of protons. In other words, hydrogen has a different positive charge than helium, which is different from lithium and beryllium, etc. And what Moseley recognized is that if we arrange the periodic table not by atomic mass, but instead by this atomic number, the number of protons, this gives a much clearer periodic pattern than if we ordered it by atomic mass. And so Moseley recognizes that Mendeleev and the other chemists of his time that had done this work, that most of their ideas were basically correct. It's just that we shouldn't order the elements by their atomic mass. We should actually order them by their atomic number. Which leads us to a statement of the modern periodic law that simply states that the properties of the elements are periodic functions of their atomic numbers. So in other words, whenever we order the elements by their atomic numbers, which that's how our periodic table is still organized today, 1, 2, 3, 4, 5, 6, 7, etc., that when we order them by that atomic number, the properties of those elements, they repeat in a predictable pattern. And more specifically, every 8 elements or so. And there are some exceptions to that, as we'll see in class, but that is a very predictable pattern, though, that we have based on that property. So in this video, we have looked to recognize and explain why there was a need for an organizational system for the elements and their properties due to the advancement of chemistry and technology and science in general from the 17 into the 1800s. We looked at some of the early periodic tables and how those came to be from Newlands and Meyer and Mendeleev. And then finally we looked at the modern periodic law and differentiated that from Mendeleev's that Moseley showed us how that should be done.